So let's remind ourselves, a vector is usually written as a pair of numbers, but I want you to see the pair of numbers as like an instruction for a move. So the vector v equals ab uh, can be seen as follows. You start at the origin, you move a units horizontally, and then you move b units vertically. So this algebraic object and this arrow, they mean the same thing, but represented differently. So the first habit we're going to make is to think of vectors not only as algebraic objects as such, but rather also as arrows, where the tip is the point we arrive at if we move A units horizontally and B units vertically. So for example, if we move 3 units horizontally, and then we move 2 units up vertically, we arrive at this tip and we get respectively this vector. So for the sake of simplicity and convenience, we will introduce two vectors. We're going to call them E1 and E2, and these are going to be the vectors 1, 0, and 0, 1. And if we do this, if we define these vectors, then we can represent any vector AB as a linear combination of these vectors, because we already agreed that the geometric meaning of the vector AB is that we're going to move A units in the direction of E1 and B units in the direction of E2. Therefore, a vector like 4, 3, for example, it can be represented as 4E1 plus 3E2, and the 4 is telling us how much of E1 we have and how much of E2 we have. So the first thing we want to discuss is addition of vectors and what does it mean geometrically. So let's recall that real quick as well. So remember, when we add two vectors, we add them component-wise. But what is happening geometrically? So the reason is very simple. The horizontal parts add up and the vertical parts add up. This is all we're doing. So if we have two vectors, u and v, this basically means move 1 unit horizontally, and then 4 units horizontally, and then move 3 units vertically, and then 1 unit vertically, and you arrive at this step over here. And thus the resultant vector u plus v is this diagonal of the parallelogram, and that's going to be always the case. And using this geometric visualization, we can easily see that doing u then v or doing v then u lands at the same final point. The final point is the opposite corner of the same parallelogram. So the next thing we need to recall is the definition or the geometric intuition behind subtraction of vectors. And this is quite interesting. This is more interesting than vector addition. So for that, let us recall that if we have a vector v and we hit it by a minus, what we're doing is that we're reversing the arrow. So if we have an arrow, we're gonna reverse that arrow. Um, uh, so if you think about minus v in this way, you can see that u minus v has a very useful meaning. Um, Geometrically, it means it is the arrow that starts at the tip of v and ends at the tip of u. So let me say that again. It is the arrow that starts at the tip of v and ends at the tip of u. So subtraction measures the move from one vector tip to another. So this is a very nice way to think about vector subtraction. Indeed, you can also think about it as a vector addition. Like if you rewrite u minus v as u plus minus v, you can apply the parallelogram trick and the reversing the vector trick to see where u plus minus v lands. Next comes scalar multiplication. So multiplying a vector by a number does not change its line. It only stretches, shrinks, or reverses the vector. If v is equal to v1, v2, then cv is equal to cv1, cv2. Here's a useful way to think about what's going on. If we introduce the set of vectors where we take v and we multiply it by t and let t run over all the real numbers, what happens is that we get a line that goes in the direction of v and it goes through the origin. So we get this line that is parallel to v through 0. Um, when t is positive, tv goes points in the direction of v, and when t is negative, tv points in the opposite direction. And when t is 0, we just everything collapses to the origin. So scalar multiplication is the geometry of staying on the same line. Once we understand how we scalar multiply, we can easily understand lines themselves because basically any line is a point and a direction. So if we know that a line passes through a point P and we know that it goes in the direction of a vector V, then any line can be written as P plus TV. This is very important because this is a different way to think about lines in 2D. So, for example, if we look at all of the points of the form 1, 1 plus t, 3, 1, this means we're talking about the line that passes through the point 1, 1, and that goes, so it passes through the point 1, 1, and it goes parallel to the vector 3, 1. So if we look at the vector 3, 1, 1, 2, 3 units, and then go 1 up, we see that we're going parallel to that vector v, and we're passing through the point 1, 1. So once we understand this, we can now better understand the meaning of linear dependence. So remember, two vectors are linearly dependent if u is a scalar multiple of v or v is a scalar multiple of u. So geometrically, this means that the two vectors lie on the same line through the origin. They may have different length, they may even point in opposite directions, but they do not give two genuinely different directions. So if we have two vectors where one of them cannot be stretched or reversed to reach to get the other, then they're necessarily independent. So, for example, as long as the two vectors, for example, fall on this line, any two vectors that fall on this line are dependent. However, if we take any vector that fall on this line and this vector, we can clearly see that they're not dependent because if they were dependent, they must have been on the same line. So one way to think about linear dependence is to think about it as a notion of collinearity if we assume that all vectors start at the origin. Our next notion that we want to give a geometric meaning is the notion of a norm or a magnitude of a vector. Remember, if we have a vector v equals to v1, v2, then we define its norm or magnitude to be the square root of the sum of squares of the components. However, this comes naturally from Pythagorean theorem. So let's take an example. Let's look at the vector 3, 4. We know that the norm of this vector is the square root of 3 squared plus 4 squared, which is 5. However, what does that mean geometrically? So geometrically, what's happening is that, remember the vector 3, 4, it's the vector we obtain by moving 3 units horizontally and 4 units vertically. However, we know that the vector is going to be always the hypotenuse of a right triangle as such, whose legs are the coordinate pieces. Therefore, if we simply use Pythagorean theorem, we can see that the size of the hypotenuse squared must be the sum of the squares of the other sizes. And thus we get the formula of the magnitude of a vector, of a generic vector v equals to v1, v2, to be the square root of the sum of squares. Now, the final notion we'd like to discuss is the notion of an angle. So remember, if we start with any vector v, we can quote unquote, that is any vector that is non-zero, we can quote unquote normalize that vector by dividing by its norm. We can divide by the magnitude of that vector to make it a unit vector, meaning we make it a vector of magnitude 1. You can think about applying the magnitude to this, and you will see that you will get the magnitude of v over the magnitude of v, which is thus equal to 1. So the magnitude of v hat is necessarily equal to 1. But with this observation, what we can do is that we can write every vector as its norm times v hat. So if we define v hat like this, then every vector v that is non-zero is equal to the norm of v times v hat. But the interesting part here is that the vector v hat has its tip on the unit circle. So geometrically, what this means is that since the vector v hat is of norm 1, this means that the tip of that vector, it falls on the unit circle. But since it falls on the unit circle, and we know that every point on the unit circle has polar coordinates cosine theta, sine theta, where theta is the angle with the x-axis, then the vector v hat, which is given by the coordinates of its tip, is necessarily of the form cosine theta, sine theta, where theta is the angle we make with the x-axis. And therefore, in this sense, we can give a meaning to, we can define a so-called angle of a vector. And that's going to be always obtained by rewriting the coordinates of a vector in polar coordinates. So if you think as the vector v as equal as a vector which equals x comma y, and you write x equals r cosine theta and y equals r sine theta, and you solve for r and theta, the theta, which is the angle we make with the x-axis, is going to be the angle of the vector. All right, so this finishes what we wanted to discuss in this video. And our next video is going to be about dot products and the meaning of dot products geometrically. So stay tuned for that. Thanks for watching.